in this lesson, we're talking about continuity, and we have two big things that we want to learn by the end of this lesson. We want to know what it means for a function to be continuous, or conversely, for a function to be discontinuous, and we want to be able to recognize that when we see it in a function. And we also want to be able to demonstrate that a function is continuous or discontinuous in a more formal mathematical sense. So we'll approach this concept of continuity from sort of a visual approach to get an overall idea of what continuity means, and then we'll look at it in a little bit more detail mathematically. So a function is continuous if, in simplest terms, if you can draw the function or sketch a graph of the function without lifting your pencil or your pen off of the paper. So if I am drawing a quadratic function like this, I could draw that whole thing. I didn't have to lift the pen off the board. Similarly, if I'm drawing like a sine function, let's say, I can draw that whole thing without having to lift the pen off the board. A function would be discontinuous if there is something that forces me to have a break when I'm drawing it. So a function that had, say, a vertical asymptote would be discontinuous because I would draw this function, I would have to lift my pen off the paper and draw the other part of my function over here. Similarly, things that have graphs that have holes in them are not continuous because I could be drawing along like this. I have to put a little hole in my graph like this, and then I can continue on with the rest of the function. Okay. So it's fairly easy if you see the graph of a function to recognize whether it is, and let's just label these here, these things are continuous, and these ones over here are discontinuous or not continuous. Now, what does this mean in mathematical terms? Mathematically, there are three conditions that have to be met for a function to be said to be continuous at a specific point x equals a. So at that point x equals a, the function has to exist. Second thing that has to be true, the limit as x tends to a of that function must also exist. And the third thing that has to be true is that that limit as x tends to a of f at x has to be equal to the value of the function at that point. If those three things are true, then the function is continuous at that point x equals a. Now, we say that a function is continuous on an interval if it is continuous at every point on that interval. So these functions that I drew over here on the left-hand side, these are continuous for all real numbers. These functions that I've drawn over here on the right that are discontinuous could be continuous for a particular interval. If we're looking at this red function and I was just looking at the interval from here to here, it's continuous on that interval, but it's not continuous everywhere on the domain of the function. So let's just look at a couple more examples here graphically. So here we've seen this graph before when we were talking about whether limits existed or not. Where is this function discontinuous and why is it discontinuous at that point? Well, obviously there's a number of points here where this function is discontinuous. The first one is here at x equals 1. Now, we don't want to say that it's discontinuous just because there's a gap in the function. We want to connect it back to those three conditions necessary for continuity that we talked about up at the top of the page. So at this point, x equals 1, the reason that this is discontinuous is that the limit as x tends to 1 of f at x, that limit exists because as we approach from the left and the right, both sides of that curve are approaching the value of 1, but that limit is not equal to the value of the function. The value of the function at that point is 2 rather than being equal to the value of the limit. The next place it's discontinuous is at x equals 2. Why is it discontinuous at x equals 2? Well, the function exists. The first condition is satisfied because of that black dot there. But the second condition, that the limit has to exist, so the limit as x goes to 2 of f at e, does not exist. So that's condition 2 is not satisfied. Limit as x tends to 2 of f at x does not exist. It's discontinuous at x equals 4 because f at 4 does not exist. That was the first condition we talked about. There's no filled in spot there at x equals 4 to indicate the value of the function. And finally, it's discontinuous at x equals 5 for a couple of reasons, but if we go through that list from top to bottom, the first one is that the value of the function does not exist at that point because it's a vertical asymptote. The function does not exist at a vertical asymptote. Also, the limit is not going to exist, but going through that list from top to bottom, that would be the first one that we come to. Is the function continuous on the closed interval 2 to 4? Well, let's see. 2 to 4 is from here to here, and by closed interval, it means that we include the endpoint. So we're including x equals 2 and x equals 4 are included in that interval. So the answer, of course, is no, because our function is not continuous at x equals 2 and x equals 4 for the reasons we outlined up above. Is the function continuous on the open interval 2, 4? Now, the open interval from 2 to 4 does not include the endpoints. So it does not include x equals 2 and x equals 4. So if we exclude 2 and 4, we're really just looking at what's happening from here to here, and from there to there, I can draw this little section of the curve here in one smooth motion without taking my pen off the paper here. There are no places where there are gaps or discontinuities, so it is continuous on that open interval. Okay, so a second example. This is the kind of thing you want to be able to do. Determine whether the function f at x, which is defined as negative x squared plus 4 if x is less than or equal to 3, and 4x minus 8 if x is greater than 3, is continuous at x equals a. And you want to be able to do this using those three conditions necessary for continuity that we talked about on the top of the previous page. And you want to be able to just go through these things in order. So number one, the first one was, for it to be continuous, the function had to exist at x equals 3. So we want to calculate our value of f at 3. If we're doing f at 3 here, we need to use this part of the function right here because it works for x is less than or equal to 3. So we're just going to sub in 3 there. We get negative 9 plus 4 is negative 5. Our second point was the limit has to exist at x equals 3. So let's check to see if our limit exists. We're going to do this by doing the limit as x tends to 3 from the left, and the limit as x tends to 3 from the right of f at x. If we're approaching from the left, we want to use, or we're going to want to evaluate this limit, x tends to 3 to the left of negative x squared plus 4, because that's the branch of the function that we're using. We can evaluate this limit using direct substitution. So let's sub in our 3 squared plus 4, and we get negative 5. For our right-handed limit, we need to use the other branch of the function because we're approaching from values of x that are greater than 3. So we're going to do the limit as x tends to 3 from the right of 4x minus 8. Again, we can evaluate by direct substitution. This is 4 times 3 minus 8 is 4. Okay. Our limit as we approach from the left and our limit as we approach from the right are not equal to each other. So we can say that the limit as x tends to 3 of f at x does not exist. So that second condition necessary for continuity is not satisfied. So we can say f at x is not continuous at x equals 3. Now, if that limit had existed, then our third step would be to compare the value of the limit at x equals 3 to the value of the function at x equals 3 and see if they were the same thing. If they were the same thing, we would conclude that it was continuous. But once one of these three conditions fails, we have to say that it's not continuous at that point. And we can confirm this by looking at the graph of the function. The graph looks like this. You can see the quadratic function going up to x equals 3, and this big jump discontinuity here at x equals 3 between the two branches of our function. All right, our last sort of question that you might be asked about this kind of stuff. For what value of k is the function f at x equals, and again, it's a piecewise function, x squared minus 2x for x less than or equal to 6, and 2x plus k for x greater than 6. For what value of the k is this function continuous at x equals 6? Again, we want to use those three conditions that have to be true for the function to be continuous. Number one, the function has to exist. So let's start by finding the value of f at 6. We're going to be using this value up here, so that's going to be 6 squared minus 2 times 6 is 36 minus 12, which is 24. Okay, so we know that the value of the function at 6 is 24. If the function is going to be continuous, the limit as x tends to 6 of f at x must also equal 24. So the limit has to exist and it has to equal 24. For the limit to exist, the limit as x tends to 6 from the left of f at x must equal the limit as x tends to 6 from the right of f at x, and both of those are going to have to equal 24 as well, because they have to equal the same thing and the limit has to equal 24. So let's take a look at these two one-sided limits here. The limit as x tends to 6 of from the left of f at x is going to be the limit as x tends to 6 from the left of x squared minus 2x. And the limit as x tends to 6 from the right of f at x is going to be 2x plus k. Now, this is the one here that we want to work on because it has our value of k in it. We know that that has to equal 24. So let's start evaluating that limit. We can do it by direct substitution. I'm going to sub in that value of x. I get 12 plus k equals 24. Solving that, I get that k is going to be equal to 12. So that's the value of k that we need in order for the function to be continuous at x equals 6.